Hey everybody. I've got up a reminder of what we talked about last time, our definitions of the sine and cosine functions, right? They've got this convoluted definition. You got a set of a coordinate system with a horizontal and vertical axis. You throw an angle in standard position with its vertex at the center of that coordinate system. You have a unit circle whose center is also at the origin of that coordinate system. And then you see where that angle intersects the unit circle. And the x coordinate, the horizontal coordinate of that intersection point, is the cosine, the value of cosine of that angle. And the y coordinate is the value of sine. So with these two definitions in mind, these are kind of base definitions, we can make we have several other trigonometric functions that are defined in a similar way with exactly the same setup. We just have different configurations of these x and y coordinates. So let's go through these other four definitions. We have a function called the tangent. The tangent of t will be the y coordinate divided by the x coordinate. Or you can see that this means we're looking at sine of t over cosine of t, right? And this is provided that the x coordinate or the cosine is not zero, right? So here's an example of a function with some problems in its domain. Remember, the cosine and sine functions we saw last time have as their domain all real numbers. The tangent does not have the same domain because there are several places where the cosine is zero. For instance, at pi over 2, we know the cosine of an angle of pi over 2, that's our vertical, our right angle with the horizontal. And so at that intersection point, it's 0, 1, the x coordinate 0. So tangent's not defined there. And there's an infinite number of places it's not defined, every place where the cosine is 0. We also have the secant, which is going to be 1 over x, or 1 over the cosine. And again, this is only defined where x is not equal to 0. So it has the same holes in it that tangent does. Whenever cosine is 0, secant is not defined. Let's see, we will do next, let's do cotangent of t. This is going to be x over y, or cosine of t over sine of t. And this is only defined as long as y is not 0. So in the same way that tangent and secant weren't defined when the x coordinate is 0, in other words, whenever that intersection point is along the y-axis, cotangent is not defined whenever the vertical coordinate is 0, and that's going to be whenever our intersection with the unit circle is along the horizontal axis. So for instance, if the angle is 0, we know that the sine is also 0, right? At an angle of 0, we're intersecting right at this point here. The sine would be 0, and so cotangent would not be defined. And one more, cosecant of t is going to be 1 over y, which is 1 over the sine. And again, this is not defined when when sine is 0 or when the vertical coordinate is 0 in this unit circle construction. Okay, so these are the 6 trig functions, right? So sometimes we think about sine, cosine, and tangent as our base set of functions, and then secant, cotangent, and cosecant are reciprocals. Each of them are reciprocals of one of those. Okay, sine and cosine both have domains of all real numbers. The rest of them have domains that are all real numbers, except for there'll be places where there are holes in them. We'll go into more detail about that later. Okay, let's go ahead and compute some of these. Let's start with, let's come over here. Let's do the tangent of 4/3 pi. Okay, so I'm going to start with a unit circle. 4/3 pi is one of the ones that's on that unit circle you may have a copy of. I don't have that copy handy, so let's see what we can do here. So first, I think I'll put in some angles here. I'm not going to draw each ray for the angles. I think I'll just put in the intersection points, the important intersection points. So let's see, we'll have pi over 6, pi over 4, and pi over 3. Here's our 0. There's pi over 2. So this one's at 1, 0. Here, where theta is equal to pi over 6, our coordinate points are going to be √3 over 2, 1/2. And here, where theta is equal to pi over 4, our coordinate points are √2 over 2. Here, where theta is equal to pi over 3, our coordinate points are 1/2 √3 over 2. And then at the top, at pi over 2, it's 0 over 1. So we did pi over 4 yesterday, or yesterday is meaningless in this on these videos, but in a previous video, we did pi over 4. The other ones I'm writing from memory, just from having seen that unit circle so many times. So at some point, you should be starting to become familiar with these. None of these, of course, are 4/3 pi, but let's look more closely at one of these. So like I said, I didn't draw in the ray for each of these, but I'll draw, oops, I missed. Let's erase that. Oops. Oh, he wants to erase the whole circle. All right, let's not erase it. Let's just pretend that that dot was right there. So there's my 4/3, or my pi over 3. All right, it's not a perfect drawing. Well, where's 4/3 pi? Well, 4/3 pi is pi plus 1/3 pi, right? Pi is 3/3 pi, so if you have 3/3 pi and then another pi, another 1/3 pi, you'll have 4/3 of pi. So in terms of angles, that means I'm starting at 0, going halfway around. That's an angle of pi, and then another 1/3 pi. Right? And so something like this. This drawing is not perfect. I think my 1/3 pi was a little too big to begin with. But anyhow, this is an approximation of what we have there. So what's of most importance is that this angle in here is an angle of pi over 3. It's the same angle we have our original angle. This is one of those reference angles we're talking about, right? So I'm just looking at the portion of this after we do this first pi. There's an extra pi over 3. Also notice that the difference between this pi over 3 and 4/3 pi is exactly pi, right? If we start at this original angle and then do another pi, we end up here. In other words, this is a straight line right here. I think it's simple enough to see that this vertical distance here and this horizontal distance here are going to be the same as this horizontal distance here and this vertical distance here. I know it's making this drawing horrifying, but that's what we have. So you can imagine just rotating this triangle around down here. So if those distances are the same, that means these coordinates are the same. Notice they're just both in opposite directions. So this is another thing we did in a previous video, talked about using these quadrant 1 values of our common trig, our common angles. We can get other values. So I know now with this knowledge, 1/2 and √3 over 2, this must be in the opposite direction, -1/2 to the left instead of the right, and √3 over 2, but negative because we're going down instead of up. And there are the x and y coordinates of that point, right? So with those x and y coordinates, we can now answer the question that was asked. And in fact, let's just answer a few more questions. We know the cosine of 4/3 pi. is the x-coordinate. The sine of 4/3 pi is the y-coordinate. The tangent of 4/3 pi is going to be the y-coordinate over the x-coordinate. The x-coordinate's not 0 here, so we're fine to do this. So that's negative √3/2 over negative 1/2, which the negatives cancel, the 1/2s and the denominators cancel, and we get a √3. We can also do, I'll just do them in the same order we have over here. Secant of 4/3 pi. This is 1 over the x-coordinate, which is, of course, just the reciprocal, so -2. What's next? Cotangent of 4/3 pi. This is going to be the x-coordinate, -1/2, over the y-coordinate, -√3/2. And if you reduce this or manipulate this fraction, the negatives cancel, and we'll get 1 over √3, the reciprocal of tangent, as we should expect. Let's make that root look like a root. Some people like to write this as √3/3. I find either to be acceptable. And then one more. What have I not done? Cosecant. Cosecant of 4/3 pi is 1 over the y-coordinate, or -2 over √3, or as some might insist, -2 √3/3. Okay, so there are the 6 trig functions for that angle of 4/3 pi, right? So it's the same as the cosine and the sine. We know the definitions. We can easily, if we are given some values on the unit circle, it's easy enough just to plug them into the definition to get the values we want. All right. So let's go to a new page. Let's look at something else here. Let's take a look at the tangent, pi/2. Okay. So again, I'll draw myself a nice unit circle. Let's make this one kind of big. We're going to do some drawings on this. Here's my circle. All right, that looks fairly well. All right, so an angle of pi/2. That's like this. There's pi/2. So we know the coordinates of this intersection point are 0, 1. And remember, tangent of pi/2 is going to be the y-coordinate over the x-coordinate, which is 1 over 0, which is not defined. Okay, so oh, sorry, I just completely lost my place for a second. Sorry. Tangent of pi/2 is not defined because we have a 0 in the denominator. I wanted to give us another way to interpret the tangent that makes this just another way to see what's happening here. There's actually 2 ways we can think of to see this. One interpretation of the tangent, do a quick sketch of the unit circle. All right, so I've got my angle and this ray right here, and this is the point y over x, xy, and the tangent is equal to y, tangent of, let's put an angle in here, tangent of theta. Tangent by itself doesn't really mean anything. Tangent of theta is going to be y over x. Notice this line, the terminal ray, if this were a line, its slope would be the change in y over the change in x, which means we have to take the difference between two coordinate points. Well, the only other point we know for sure is the origin. So its slope is y minus 0 over x minus 0, or y over x. In other words, the tangent is telling you the slope of the terminal ray of the angle. If we think of it as a line, an infinite line, we can compute its slope, and it's going to be exactly equal to the tangent. Well, the terminal ray in this pi over 2 angle is a vertical line, and we know that vertical lines slopes are not defined. And so it gives us a pretty good geometric interpretation of why this happens, why we have these holes. And it also lets us know that if we continued to rotate around, if we had an angle of 3 pi over 2, which is pointing straight down, we also have the same issue, right? And if we continue rotating around, so 5 pi over 2, and so on, anytime you do an angle that ends up in either one of these vertical places, you'll get a hole in the tangent function, right? A place where it's not defined.